Alright, so this presentation is on Sanger sequencing, and before I go into detail about how Sanger sequencing works, I will first simply define what Sanger sequencing is. And Sanger sequencing is simply a method of determining DNA sequences. It was first developed by Frederick Sanger in 1977 and remained the most widely used method for DNA sequencing for around 30 to 40 years. And the purpose of Sanger sequencing is to obtain information of medical value from either a patient or an individual's genome. And how does Sanger sequencing work? Well, it breaks down into three main steps. The first being polymerase chain reaction, or PCR, with fluorescent chain terminating nucleotides. And I'll go into detail as to what that is and how it works in the next few slides. So then after the first step, you will end up with segments of your sample DNA of varying length, which you throw into a gel electrophoresis, and then on the third step you simply analyze the gel in order to determine the sequence of your sample DNA. So the first step of the automated version of Sanger sequencing is PCR with fluorescent chain terminating dideoxynucleotide triphosphates, or DDNTPs. So what DDNTPs basically are fluorescently labeled nucleotides or glowing nucleotides. And so the way it works is that you start with a sample DNA strand, and what you want to do is amplify it with PCR in order to make many copies of this sample. And with all of these copies, you then heat it up in order to denature the strands. So then you'll end up with your template strand, or the single strand that you see on the bottom. And then with this, you would then separate all of the template strands into 4 separate samples. And in these samples, you will add all 4 nucleotides, that is adenine, thymine, cytosine, and guanine, as well as one of each nucleotide, but it is also fluorescently labeled. So then with this, once you add it into the sample, there will be a primer and polymerase that will start building a complementary strand on your template strands. And every time the complementary strand attaches a glowing nucleotide, it will then terminate the strand and then continue to make more segments of DNA like so. So then you end up with segments of varying length from each of these samples, and this one is for adenine, and then you'll get one for thymine, cytosine, and guanine. So as you can see here, for each sample you end up with segments of different lengths for each sample. So then after step 1, you'll end up with segments of DNA of varying lengths, and then you throw all of these into gel electrophoresis. So in the automated version of Sanger sequencing, there will be a computer with a laser that basically reads the fluorescent labels on each of the nucleotides or segments, and then it will simply print out for you what the sequence of your sample DNA is. However, in the manual version of Sanger sequencing, you will get something like this after performing gel electrophoresis on your sample. And so the way you read this is from bottom to top. The segments at the bottom are the shortest, whereas the segments towards the top are the longer segments of DNA. So in this example, you would read it as CAGCG and so on, and that will be how you obtain your DNA sequence from your sample. So my partner will now go on to talk about challenges in Sanger sequencing and discuss alternatives like next-gen sequencing.